All right, let us begin the MSCF program's Programming Prep course. This is the first of the non-credit, but nevertheless required, preparatory courses that you'll take during July and August to make sure that everybody has a solid background necessary when the main courses in the program begin at the end of August. So in the Programming Prep course, we're going to talk about the Python programming language and some important data structures, programming facilities, and algorithms that you can use in a Python program. Welcome to Carnegie Mellon's MS in Computational Finance program, and congratulations for being accepted. For many of you, this is likely to be the hardest that you have yet worked, which many of you may find very difficult to believe, but trust me, it's true. You can think of the MSCF program as quant school. What we're teaching you is the basic skills that you need in order to function as a quant in the financial industry. And this is going to include a variety of skills, including being able to compute correct prices for a variety of financial derivatives, such as puts and calls on stocks and commodities and bonds and various things. You're also going to need to have a good handle on understanding and measuring risk of loss of your various investments. Increasingly, the job of a quant is to use data science and machine learning knowledge to investigate huge volumes of data and try to identify interesting and profitable investment opportunities in the data. So being a quant requires both broad and deep knowledge in a variety of areas. First of all, you have to understand finance and economics. The point here, after all, is to make money and preferably not lose money in the process. You're going to need to know what kinds of investments exist and what markets these are traded in. You're going to need to have a very solid foundation of what we might call conventional undergraduate mathematics and statistics, that is, things like linear algebra, calculus, probability, and statistics. And you're going to need to have a good understanding of those ideas pushed to a higher level, namely data science and machine learning, how to use random number generators and statistics to simulate the evolution of investment prices and compute prices based on these simulations. You're going to need to understand stochastic calculus, in which the ideas of calculus and probability and statistics are combined. And because unfortunately we can't always get exact analytical answers to our problems, you're going to need to understand how to use numerical methods to compute very close approximations. And critically, it's not going to be enough to be able to do all of this on pencil and paper. As a quant, you're going to have to write code. So programming is a key part of this training. Python, in just the last couple of years, has emerged as the most important single language to know well if you want to function as a quant in the financial industry. Python, unfortunately, is pretty slow. And so if you need your code to be a lot faster than Python, you may find yourself having to write things in C++ or Java or some other more traditional object-oriented language. Excel and VBA is still very heavily used in the finance world. SQL is very commonly used for accessing sources of data. And a probability and statistics package called R is also something that you'll very likely encounter and need some exposure to. So we're going to mostly concentrate on Python here, and you will probably have some exposure to several of these other things as the MSCF program progresses. Okay, so we assume that you have completed at least a one-semester course in some widely used object-oriented programming language such as C++ or Java. Perhaps your background is in Python itself. If you've done almost no programming, or if you didn't do very well in the one semester course that you took, this is going to be a problem for you, frankly. Coming into the MSCF program, we have people with a very wide variety of programming backgrounds. We do have people who have only taken 1 or 2 semesters of college-level programming. We have other people who have computer science degrees, for whom a lot of programming will be relatively easy. And we even probably have people who have a few years of professional programming experience. And yet, regardless of what level you're starting from, you are going to need to develop a significant level of competence with the Python language and a variety of programming techniques that we're going to discuss. So, we assume that you understand low-level data types such as numbers, character strings, Boolean or true-false values. We assume you understand what a variable is and what assignment is. We assume you know how to do arithmetic, that you know how to compare values and do logical operations like and, or, and not. We assume that the idea of a decision or the idea of a loop is very familiar to you, and that you have made use of functions that receive argument values into parameter variables and that also return values when the functions have finished doing their jobs. We assume you understand what a data type is, both the built-in data types at the low level of your language, like integers and floating point numbers, and that you've also had exposure to user-defined data types called classes, and that within this arena of object-oriented programming using classes, you know what inheritance is, and you know what polymorphism is. Now, you may not be completely familiar with all of these ideas, but you should be pretty familiar with most of these ideas and at least heard of almost all of these ideas. So, Python has been the fastest growing programming language in a variety of different areas for several years. And in particular, for quant work, it has, just within the last year or two, become more or less the dominant language. Now, for things that need to be very efficient, C++ is still perhaps a better choice. For a lot of so-called infrastructure work, with just running the operation of a big bank or trading firm, Java is very heavily used. The advantage that Python has is that it's very easy to read and write very powerful programs, and there's a huge number of add-on modules that you can use with Python, such as NumPy, Pandas, Matplotlib, TensorFlow, and so forth, that give you mathematical, probability and statistics, spreadsheet operations, data science, and machine learning capabilities that are quite powerful and easy to use. Now, Python is not the only game in town. It is a relatively young language compared to a lot of other languages that you've probably encountered. For example, the R statistical environment that many of you may have used does have superior visualization for statistical results. Python is rapidly catching up, but if you need something quite sophisticated, R may be a better bet for that. Languages such as C++ are, potentially at least, much more efficient and much more mature object-oriented programming languages. In fact, some of the most important facilities used in Python, such as NumPy, is actually written in the C language for very high performance. And in fact, the most widely used Python environment is itself actually a C program. You'll find, despite its age, that Excel using VBA is still very widely used. SQL for accessing database systems is widely used. Some firms, such as Goldman Sachs, for example, have their own proprietary programming languages that you will have to learn if you are hired by such a firm. We are going to start out in the MSCF program using Python, not only for this preparatory course, but for the Financial Computing 1 course that immediately follows this course. And we are going to have a so-called mini semester that is a half a semester course in the C++ programming language in the early part of the spring. So between those two languages and whatever other languages that you may have used, hopefully you'll have a good leg up on learning any programming language that you might need to in the future. Okay, so what about Python? Well, you can use it to write top-down style programs where you start out with a task that you break down into a sequence of steps, and then you break each step down into a sequence of sub-steps and so forth. That's a sort of older style of programming that was very common through the 1980s or so. Or you can use Python to do full-blown object-oriented programming where you're creating data types of your own, and these data types have specific interfaces that you can talk to and so forth. Now, Python is easier to write than most other conventional languages. It has a much lower level of sort of boilerplate stuff that you have to write in order to get your program to work. On the other hand, the access rules within Python are so loose that for really large, really fast, really long-term projects, Python may be not the best way to go. But that's significantly a matter of opinion, so I won't say more than that. Now, the language is actually named for the Monty Python comedy troupe, not for the snake, although if you look at documentation for Python, you will see that it has a little stylized snake as its logo. Okay, Python was originated by a fellow named Guido van Rossum, who has been appointed the Python BDFL, the Benevolent Dictator for Life. This is a fairly common term in Python world. You'll see other people designated as BDFL for various modules or packages that they have written. There are two versions of Python currently in use. There's version 2.x. That is still in use, and there are some libraries that will only work in Python 2.x, but that's becoming increasingly rare. And everything that we need works in this more recent version called Python 3.x. In particular, we're going to be using Python 3.7, which you can get and install as part of Anaconda 2019.03. So this was something that was released by the Anaconda organization in March of this year. There's a video that I've posted in an announcement that will show you how to go about downloading and installing Anaconda, and you want to make sure that you choose the Python 3.7 version of the Anaconda installation. All right, so let's actually start doing real things. I have installed Anaconda on my system, and on the right side of my screen I have an Anaconda PowerShell prompt showing. Now I'm going to be using one of the most old-fashioned integrated development environments for Python called idle. You should try out idle, but I recommend that you become acquainted with something more powerful and more convenient, such as Spider or PyCharm. I prefer to use idle for my lecture videos exactly because idle is so simple. It doesn't have a lot of icons on the screen, a lot of text boxes and symbols and sub-windows and so forth on the screen. So it doesn't take up much screen real estate when I'm recording a video. All right, so I'll type idle and press enter. And what I get is initially a shell window. Now in the shell window, you can directly type Python code, and the Python shell will interpret that code for you. So it's a bit like a command shell, such as you might encounter in Linux or on a Mac, or the C: arrow prompt in a Windows command window. But this shell executes Python code rather than executing system commands. All right, so let me get this positioned correctly in my video screen here. Okay, there we go. So I've made this thing the right size that I can start interacting with it and it'll be properly recorded. Okay, so notice that this is Python 3.7.3. If you have something more recent than Python 3.7.3, that's fine. Anything older than Python 3.7.3 may behave somewhat differently from this most current version. In particular, if you have a version of Python that's older than, let's say, 3.6.5, you're probably going to run into a lot of incompatibility. So make sure that you have at least Python 3.7.3. Okay, so at this shell prompt, I can do simple things like using an assignment statement to assign the value, the integer value 123, to this Python variable j. Okay, so the assignment is done, and if I now just type j at the prompt, the Python shell will show me what the current value of j is. If I wish to get out of the shell, I can type quit with parentheses. Quit is actually a function call, and the parentheses are required. If you just type quit, here's a very annoying thing that's popular for programming. Okay, so I've just typed quit, and the shell understands exactly what I'm trying to do, but rather than simply doing it, it tells me, no, you have to use quit with parentheses in order to exit. So I'll type quit with parentheses like I'm told. And now, when I press enter, I get asked for confirmation. My program is still running. Do I want to kill it? If I clicked OK here, I would find myself back at my Anaconda PowerShell prompt. But rather than doing that so that I have to fuss around re-establishing this window, I'm just going to press cancel and remain in my shell. Okay, now in the slides here, you may have noticed that I have a pound sign or sharp sign or hash mark or tic-tac-toe sign, or people have a variety of different names for that symbol. That symbol in Python introduces a comment. And everything from that sharp sign to the end of the line, or pound sign to the end of the line, is simply ignored. So I can say j gets 1234, change the value of j as a comment, and the comment is seen by the shell but just thrown away. So the upshot of that statement is that j now refers to the value 1234 instead of 123. You can create a variable in the Python shell or any Python program, I should say, by simply giving the name of the variable, x, for example, and using an equal sign to assign some value to that variable. The first letter of your variable name has to be either a letter or an underscore. Now, the letter could be lowercase or uppercase, and in fact, those are distinct from each other. Following that letter or underscore, you can have more letters, more underscores, and you can also have digits. That is, digit characters between 0 and 9 in your variable name. So here, I haven't pressed the enter key yet, so let me do that. And I have now created a variable named x. And this variable named x is referring to the floating point value 12.7, as opposed to the integer value that j is referring to, 1234. Okay, so x is a legal variable name, j is a variable name or variable... Sorry. X is a legal variable name, j is a legal variable name, x underscore 2 is a perfectly legal name. True is a Boolean value. Notice that that's true with a capital T. And so I now have this legal variable name x underscore 2 referring to true. If I put a digit first, or if I put something that's anything other than a letter or underscore first, that is not a legal variable name, and I will get yelled at that I have created a syntax error here. Okay, now I'm using so far the idle shell, and I'm just typing code to the shell, and anytime I type just a value like 1.234, the shell shows me the value, or if I type a variable that refers to a value, the shell shows me the value that that variable refers to. Now, if I attempt to use a variable that doesn't yet exist, that is, that has not had a value assigned to it, I will get told that that variable name is not defined. So that's an error. For very simple things, interacting with the shell is fine. But for most situations, we're going to want to create stored programs that we can execute over and over, and that we can also make modifications or enhancements to, and that we can debug, that is, that we can fix. So, another thing we need to be able to do within idle is to run the editor, and I do that by saying File, New File. And what that does is to create a program file. I need to shrink it down so I can put it on the screen here. Here we go. So here is a program file. Notice that it is untitled at this point. And in here, if I say J gets 1234, X gets 12.5, X underscore 2 gets true, these are not executed immediately. These are saved up in a file, and I will have to save this file with a name in order to be able to run or execute this Python code. So let me do that. I'll say File, Save As. I have a directory on my system named PP 2019 Examples. So that's Programming Prep 2019 Examples. And I will simply call this thing prog1. When I save prog1, this simple-minded text editor will automatically give that file a .py extension indicating that this is Python source code. All right, so we can see now that, at least I hope you can see now, that this has been saved in my pp 2019 examples directory with the name prog1.py. The way I would execute this program now is to click Run and Run Module. What happens is when I run the module, that will actually restart my shell from scratch. Now the window doesn't disappear, it's just that the current understanding of variables and so forth that the shell has is wiped out. And I now execute from scratch the statements contained within that program file, prog1.py. You'll notice that I didn't get any output. Okay, and the reason for that is that my program file is not behaving like the shell. That is, in the shell, if I just say J is displayed, and if I say X, the value that X refers to is displayed. But that's not the case when I'm in a stored program file. In a stored program file, I have to call a function named print in order to display output. So I will have to say print J, print X, print X underscore 2 in order to see these values that I've created for these three variables. All right, so I'm going to say File, Save, and then Run Module, and this time the three print function calls do display the values for j, x, and x underscore 2. Okay. So in the interactive shell, the value of an expression is displayed automatically, but that's not the case in a program. I've created these three variables, x, j, and x underscore 2, referring to int 1234 and floating point 2.5 and Boolean true. In this next example here on slide 15, I'm going to create a variable called s, and I'm going to assign the string hello as the value that s refers to. So now I can simply say s to display hello in the interactive shell, but in my program, I would have to, I can create s to contain, or to refer to, I should say, the string hello, but then I need to say print s to cause that thing's value to be displayed, to cause s's value to be displayed. Now, you'll notice if you go to the Run menu and come down to Run Module, it has a shortcut key, F5, so rather than using that menu, I can, after I save the file, just press F5. And there we are. So now I have the values being displayed by 4 print function calls. The value of j is 1234, the value of x is 2.5, the value of x underscore 2 is true, and the value of s is hello. The print function can display multiple values. You simply give the values separated by commas, and the default behavior of the print function then is to display a space character for each comma. So I have, here I'm creating a different variable, a, referring to hello. Now s still exists, but now I have a referring to the string hello. And if I say print a comma Bob 11/3, that is simply division. I hope that's not a big surprise. All right, so I'm going to display the value of a, which is hello, and then where the comma is, I'm going to get a space. So then I get Bob and a space. 11/3 is computed, and the result of that computation is what print is going to display, and then a space, and then I get the Boolean value true. Now in the output, we see what I claimed. One thing I want to point out, which is something you should be concerned about, is that a digital computer, which is storing everything in a base 2 floating point format, cannot accurately display arbitrary precision floating point fractions. So here, what's being displayed is 3 point followed by about 16 sixes, it looks like, and then a 5, because the last digit cannot be represented exactly. If this were rounding, I would expect to see a 7 as the last digit in this output. But in fact, it's not being rounded. It's just displaying the maximum precision that it can, and unfortunately that last digit is incorrect. So that last digit 5, when I display a floating point value, that is as close to 11/3 as can be stored in a floating point variable in this implementation of Python. Okay, so that's the print function. Now, I've used values here, and I've said aloud what these data types of these values are, but I want to be more explicit here on slide 17. So these are 5 of the so-called low-level built-in types that we have available to us in Python 3.7. There are some other types that we won't encounter in this programming prep course that we may encounter in Financial Computing 1. But what we have is the int data type, which is an arbitrary precision integer. That is, the integers can get to be as large or, well, as large in magnitude as you wish in the positive or negative direction. We also have float. And float is not arbitrary precision. Float is a 64-bit representation of a floating point number, which is why we have these round-off problems when we get out to the 16th or 17th decimal place. S is an example of a stir. Okay, so this S, which is referring to hello, that's an example of a stir data type. And I can't bear to call things stirs, so I'm going to call these strings, even though the technical data type is stir. Sorry, click the page down by accident. Here we go. And actually, these are represented in Python in the UTF-8 character set by default. Now, UTF-8 is one of the most common data types for characters contained in web pages. It's a variable length data type that allows representations of very large character sets. Any human character set can be represented in the UTF-8 character set. It happens for we lazy Americans who are using ASCII, that is the American Standard Code for Information Interchange, that the UTF-8 character set happens to contain the ASCII 7-bit character set as a subset of its first byte. So for us, as I say, lazy Americans using ASCII, all of our characters fit comfortably within a 7-bit ASCII character, which is a simple subset of this UTF-8 character set. Okay, then we have the bool data type, which only has the two values true or false. And the none type data type, which only has the single value none. None is used for such purposes as to mark the end of a linked list or the leaves of a binary tree. None also happens to be the default return value for a function that does not have a return of a specific value. None is the one value that the interactive shell will not display by default. If I type an int and press enter, I see the int. If I type 3.456, that's a float, and I see the float. If I type howdy as a string, I see the whoops. Okay, this is an interesting accident. I pressed the backslash when I tried to press the enter key. The backslash, we'll discover later, is a command line continuation character. So the interactive shell is now patiently waiting for me to remember to type enter, which I will do, and the backslash does not become part of the result here. So I see the string, the stir, howdy, and so on. But none, by default, is not displayed. And if I want to see none displayed, I do have to use the print function. Now, I just said that none is the default return type for a function that does not return a value. Print itself does not return a value. All right, here I'm using print to display an int followed by a float followed by a boolean. And Spaces are put in between those values by default. Notice that I didn't get any value for print itself, because print, as it happens, returns none. I can see that by saying, let me say PR for print return equals print 123.45.6 true. Okay, so print executes and displays these values. PR is created. Notice I did not get any error when I said PR gets the result coming back from print. If I try to display the value of PR, I don't get any output because the value of PR is none. Okay, so we're going to see none pop up in many different contexts. All right, so we have numeric values. We have int and we have float. We would like to be able to do computations with these values. So we're going to take a look at using arithmetic operators. We're going to start out with the obvious ones that everybody knows, multiplication, division, addition, subtraction. As you're familiar with from just learning ordinary arithmetic, multiplication and division has higher precedence than addition and subtraction. So multiplication and division have the same precedence as each other, which is higher than the addition and subtraction operators. We're also going to take a look at an operator Python has for exponentiation, which is an operator that a lot of other languages you might be familiar with, such as C or C++ or Java, don't have. You can, no surprise, override the default precedence by using parentheses for grouping expressions. Now, as far as associativity, that is whether these things group together from right to left or from left to right, you're probably familiar and comfortable with the idea of arithmetic operators associating from left to right. All right? That is, if I say 3 plus 5 plus 7 as a trivial example, this is going to give me 15. And addition associates from left to right. That is, implicitly, this is calculated as 3 plus 5 quantity plus 7. Now, in fact, because addition is commutative, this doesn't really matter. We get the same result regardless. Exponentiation is an oddball, and it associates from right to left, whereas all the other arithmetic operators are from left to right. Okay, so some very simple examples. 2 plus 3 minus 4. Whoops. 2 plus 3 minus 4. Addition and subtraction have the same precedence. These are evaluated from left to right. I get 5 minus 4 is a 1. Likewise, 2 times 3 times 4. Multiplication is evaluated left to right. Again, multiplication is commutative, so it doesn't really matter. I get 6 times 4 is 24. This next one is a little interesting. 2 times 3 divided by 4. Again, evaluated left to right. So we compute 6 and then divide that by 4. Now, in languages such as C and C++, when you divide an int value by another int value, you get an int value as your result, and the fraction part is truncated. But the rule for Python is quite the reverse. Anytime you use division in a Python expression, you're going to get a float result. So, and that result is going to be as accurate as the machine can store in a 64-bit representation. So 2 times 3 divided by 4 is going to give us 6/4, which is 1.5. I'm going to repeat this business of division yielding float over and over again because it's a very important thing to keep in mind. All right, now here, if I mix operators from different precedence levels, 2 plus 3 times 4, of course the multiplication has higher precedence than the addition, so I get 12, and then I add 2 to the 12 and get 14. But I can use parentheses if I want to force the addition to take precedence over the multiplication, and this gives me 20. Okay, so here's our exponentiation operator now. If I say 2 star star 10, this is computing 2 to the 10th power. And if you're a bit of a computer nerd, you may already recognize that this is 1K. That is, it's 1024. 2 to the 20th power would be 1 meg, 2 to the 30th power would be 1 gig, and so on. So we have int to the int power there, which gives me an int as the result. If I take an int to a fractional power, okay, so we're doing a division to compute our exponent, and we've used parentheses to force that division to be done prior to that result being used as the exponent in the exponentiation. 1 over 2 is going to be the float, 0.5. And so 2 to the 0.5 power is going to be the square root of 2, which of course is a float. And here I have 1.14, sorry, 1.1, 1.414, etc., the familiar value for the square root of 2. Okay. So a fractional power results in a float result. Now, ints are arbitrary precision, which means that they can grow to be as large in magnitude as you want, either positive or negative. 2 to the 100th power is that number. We can get arbitrarily large. So if I compute 1234 to the 1234 power, so the output is so long, the output is 50 lines long, that my interactive shell here in idle was clever enough to not display the whole thing for me. But if I double click, I will see that entire huge result. Well, I will if I drag the cursor in the right direction. There we go. So here we have this huge 50-line long representation of the int value 1234 to the 1234 power. Okay, and of course, just as using a fractional power gives you a float, likewise using a negative power will also end up giving you a float. In this case, it will give me the closest float representation of 2 to the minus 100th power. Although there's going to be some serious round-off error here beyond this last digit. Now, as far as associativity, as I said, exponentiation associates from right to left, whereas multiplication and division, addition and subtraction associate from left to right, as we're used to from learning arithmetic in school. Let me show you why this associativity makes a difference, or why it matters. If I compute 2 star star 3 star star 2, we might glance at that and assume that it's left to right associative, just like the other arithmetic operations. Well, okay, so 2 cubed is 9, 9 squared is 81, but no, actually, the result that we're going to get here is 512, and that is because 2 star star 3 star star 2 is evaluated from right to left. Okay, so 2 star star 3 star star 2 is actually 2 to the 9th power, and surprise, surprise, that is 1/2 a k, 512. All right, so 2 to the 10th is 1024. 2 to the 9th is half of 2 to the 10th. If I want to force 2 to the power of 3 to be evaluated first, then again I need to use my parentheses. Okay, and these last couple of examples here I think are pretty obvious. All right, let's take a look at some examples either producing or involving floats. Now, I said that division creates a float, and in fact this is even true if you divide by 1. So 123, which is an int, divided by 1, which is an int, is obviously exactly 123, but because of the division, it's stored and represented as a float number. It is true, I'm going to skip ahead a little bit here, it is true that a float whose fraction part is exactly 0 is equal numerically to the corresponding int value. So I don't have anything really fishy going on here. The double equal sign is the is equal to test, which if you are familiar with C or C++ or Java or various other languages, you will have seen. Okay, so dividing by 1 gives me a float. Likewise, adding 0.0 gives me a float. So 1 plus 2 plus 3 is an integer 6, but if I say 1 plus 2 plus 3 plus 0.0, I now have a floating point 6.0, although again 6 is numerically equal to 6.0. Okay, and here, just as a reminder of precedence, I've got 1.1 minus 2.2 plus 3.3 times 4.4. Well, actually, the multiplication is going to occur first. So this is actually 1.1 minus 2.2 plus, implicitly, 3.3 times 4.4. And it ends up being 13.42. Now, you don't need to say 0.0 to get the floating point representation of an integer. You really just need the decimal point. So if I say 2 point to the 10th power, that is going to be a float, 1024.0. Likewise, 2 to the 10 point power is 1024.0. 2.0 to the 100th power is fine. Our system is big enough to store a float of that size. Okay, so in fact it's 1.268 approximately times 10 to the 30th power. But exponents can only go up a little over 1,000 or so, the way floating point numbers are represented on our system. So if I try to do something like 1234 to the 1230.0 to the 1234 power. Now we already did 1234 as an int to the 1234 power, and that worked fine. But this is going to give me what's called an overflow problem. That resulting floating point number is too big to fit into a 64-bit floating point representation. Again, if you're familiar with C or C++ or Java and you're comfortable with 64-bit floating point, this will make sense. Otherwise, just accept this as a rule that a 64-bit floating point number representation on your machine just can't store a value that's that big. Here are some string examples starting on slide 25. So hello in single quotes, that's one representation of a string. But it might occur to you, well, wait a minute, what if I have a string that has double quotes in it or single quotes in it, or what do I do if I need to represent quotes inside of quotes? Fortunately, Python is equally happy to let you represent a string between double quotes. And so, in fact, if your string has double quotes in it, like this next example, I can use single quotes to cause double quotes to be treated as literal characters. All right, so here I have a pair of single quotes enclosing a sequence of characters, two of which happen to be double quote characters. Okay, so that works fine. And I can go the other way around. In this next example, I have a single quote character that I'm using to create an English contraction, don't instead of do not. All right, so I'm using double quotes here because I want to be able to say don't, and that's a single quote, divide by 0. Okay, so you can use either single quotes to create a string or double quotes to create a string. And single quotes have the effect of causing double quotes to be treated literally. Double quotes have the effect of treating single quotes literally. We still have a problem, because what do I do if I need to represent a string that contains both single quotes and double quotes? All right, well, Python has the solution for us. We can use pairs of triple single quotes or pairs of triple double quotes also as a way of defining a string. So let me do the last example here on slide 26 first. What I want to represent is a sentence. He said, comma, double quote, don't go, period, double quote. And of course, don't has a single quote in it. All right, so I'll say single, single, single. He said, comma, double quote, don apostrophe t space go dot double quote, and then single, single, single. All right, so that's how I can create a string that contains both double quotes and, in this case, just one single quote by using a pair of triple single quotes around the entire thing. In the output, for whatever reason, Python doesn't like to display triple single quotes or triple double quotes in the output. So what it will do by default is it will use single quotes around the entire thing. And if there happens to be a literal single quote within that single quoted string, the special meaning of that single quote within the string will be, if you will, turned off or escaped by having a backslash character in front of it. I could have typed my string that way. I could have said, he said, comma, double quote, don, backslash apostrophe t, go dot double quote. And that would have obviously been equivalent. But generally, if you're too lazy to remember when you have to backslash or escape your single quotes and double quotes, you're better off just using the triple single quotes or the triple double quotes around the entire thing. Furthermore, these triple single quotes or double quotes allow you to create strings that are multiple lines long. So if I say, this is a test of a multi-line string, quote, quote, quote. Now, on slide 26, it's using triple double quotes for this. I've used triple single quotes for this, but it's the same thing. And again, Python's internal representation of this doesn't like to use the triple single quotes. So instead, what will happen is each of the places where I hit the enter key is going to be represented in the string as what's called a new line character. Okay, so this pair of visible characters, the backslash followed by the n, is the way that you represent a so-called new line character in your string, in your code. Now, In the interactive shell, what's displayed is essentially the source code level representation of that string. But if I were to print that, I would see what the user sees on the screen when that's printed. And when I print a string that has these new line characters in it, each new line character comes out as a carriage return on a line feed. Okay, so I have THIS. Now there's a new line here. So when I get after the is, I have carriage return and line feed, so that a test of a comes out on the next line down. Now, a test of a is also followed by a new line, which comes out as a carriage return and a line feed, so that multi-line string starts on the third line down. Okay, so this is an easy way of creating multi-line long strings in your program. Okay, well, this next slide, 27, repeats things I've sort of already said aloud, which is the shell, when you type a string, the shell will display to you essentially the source code representation of that string. But humans usually, that users in particular, who don't want to know anything about computers for the most part, users absolutely don't want to have to figure out that, oh, \n really means a new line, \quote really means a literal quote mark. No, users, when they see printed strings, want to see what they would see in a document. So here's another example. I'm creating a variable s to contain, this is a multi-line string, just 2 lines now rather than 3. S in the interactive shell is going to be shown to me in the source code representation, but if I print s, I will see human readable representation. In addition to new line, some other special characters that you can use within strings are \t, which is horizontal tab. \n, of course, is new line. The \ character itself is a pair of backslashes. So if I say print tab \t, so that's going to be the letters tab followed by a tab character, and then the characters NEWLINE followed by a new line character, and the characters AND space BACKSLASH followed by a \ character. Okay, and so here I have tab. Now, the tab stop is 8 characters wide, so following tab I have effectively 5 spaces for the tab. Then I have new line followed by a new line. Then I have and \ followed by 1 \ character. Okay, so if I want to represent 1 \ character within a string, I use 2 backslashes for that. And here on slide 29 is a list of other special characters that you can use within strings and the ASCII character set definition of these. In practice, the horizontal tab and the new line are probably the most common of these. Of course, you have to know about using a \ followed by a quote to represent a literal single quote, and a \ followed by a double quote to represent a literal double quote, and finally, of course, the \ followed by a \ to represent a \ character. Okay.